Hi everyone, my name is Akshaj. Say you have built a RAG system, right? You have chunky documents, you have embedded them, and you're doing similarity search to answer questions. It works great until someone asks a question that needs two or three facts are chained together, not just one. That's where lots of RAG systems quietly fail. Not loudly, just strong, confident answers. This video is why that happens and that alternative that is GraphRAG. We'll use one simple example the entire way through. So by the end of the video, you are not just holding definitions, you're actually seeing both approaches, trying to answer the same question, and watch one of them fail. So here we have 5 statements, okay, 5 facts on the screen. First one is Rahul works in the AI department. Rahul knows Python. Priya works for Rahul. Priya is working for Project X, and Project X belongs to Iran. 5 simple sentences. A person, their skill, their department, their colleague, that colleague's project, and who the project belongs to. Nothing complicated here on purpose. I want the difference between these two approaches to be about the method, not about complicated data. The question we'll try to answer in these both systems are: which project is connected to Python skill employees through this colleague? If you read that slowly, it is not asking for one fact. It's asking you to chain 3. Who knows Python, who is their colleague, and what that colleague is working for. The chaining is the whole story of this video. Traditional vector RAG have 3 building blocks. The first one is embedding. The second one is vector database. And the third one is similarity search. Right. Let's talk about each of these. Okay. First one is embedding. Embedding is the first RAG of any RAG pipeline. Turn text to numbers. An embedding model reacts to a sentence and outputs a vector, which is a long list of numbers, positioned so that the sentences with similar meanings end up close together in a same number space. Like Rahul knows Python and Rahul is skilled in Python programming would land near each other, even though both have different words, different wordings, because their meaning is close. The second one is vector database. All of these embeddings get stored in something called as a vector database, because specifically to do one thing first, given a new vector, you have to find the closest one that is already stored, and that is the code job. The third one is similarity search. So when you ask a question, it gets embedded too, using the same model. Then the vector database finds whichever stored chunks numerically closest to your question's vector. Those closest chunks get handed to the LLM as a context, and the LLM, using only what is given, answers. So I have an image here of a vector search, right? Here's what it looks like. For example, each of these 5 sentences become a point in space. Our question becomes a point too, and the system just grabs whichever point is closer, which is nearest, right? If you look closely, look at what actually gets retrieved. The query mentions Python and employee, so it lands close to Rahul knows Python and Rahul works in the AI department. Fine so far, right? But if you look at a chunk that actually answers the question, Project X belongs to Python, neither mentions employee. In similarity terms, they are just far away from the question. Not because they are wrong, because nothing on that wording overlaps with how the question was phrased. This is the core limitation. Similarity search retrieves chunks that read alike. It has no concept of connected through 2 steps. Each chunk is stored on its own, right, completely independent of each other. The system does not know that Priya works with Rahul. It is the bridge that makes 2 of these facts relevant. It just sees 3 unrelated sentences competing for a similarity score. So what actually happens? Either the LLM gets handed the wrong chunks, or guesses, or if you're lucky enough that all these 5 chunks get read anyway, the LLM has to do multi-hop reducing itself. That is in context with no guarantee that it connects the dots correctly. Vector RAG is not designed to traverse relationships. It's designed to find similar texts. So what's the how to solve this, right? So we solve it using knowledge graph. GraphRAG starts from a complete data structure. Instead of chunks of text, you extract structured facts as a graph. So here there are two important parts in GraphRAG. The first is nodes and the second is edges. Nodes are basically every entity becomes a node. Rahul, Priya, Python, Project X, Neuron, these all become a node. Each one is just as a labeled point, right? And edges on the other hand, and every relationship between two entities become an edge. This matters because edges are labeled. So not just Rahul connects to Python, but specifically Rahul knows Python. Priya works with Rahul. The verb is stored, not just the fact that the connection exists. So if we talk about multi-hop relationships and graph traversal, now here's the part that changes everything. To answer a question, the system does not need to find one similar chunk. It traverses. It starts with the node Python and follows the nose edge back to Rahul. From Rahul, it follows the works with edge, the verb works with edge, to Priya. From Priya, it follows the verb working on to Project X. 3 hops, 3 edges, 1 clear path. The path is the answer, not just a guess assembled from loosely related chunks. An actual traverse through explicit relationships. That is graph traversal. So, and that's what multi-hop relationship means in practice. A question that requires walking through more than one connection to reach the correct answer. And if you put it side by side, a vector RAG and graph RAG, here what you get. It does not mean that vector graph RAG is a better version. It has real costs and most questions don't need. So you may ask that where does plain RAG is sufficient? If your question is a direct factual lookup, like what is Project X, what does Rahul know, a single relevant chunk answers completely, no chaining is required, and that is where vector RAG shines, because vector RAG is simpler to set up, cheaper to run, and honestly the right default for most retrieval problems. Document Q&A, FAQ bots, semantic search over a knowledge base, vector RAG handles the vast majority of that pretty well. And if you ask that where GraphRAG earns its costs, GraphRAG is worth it when your questions are fundamentally about relationships. How X is connected to Y, who influenced whom, which teams touch these systems indirectly. So compliance and dependency mapping, fraud or anomaly detection, where pattern is the connection, research questions that require chaining facts, and that is why GraphRAG is best used. The trade-off is real. So building a knowledge graph means that extracting entities and relationships upfront, which is more setup work than just chunking and embedding text. The honest way to decide, if you ask me, is that if you can answer the question by finding one good passage, you use vector RAG. If your answering requires connecting 2 or more separate facts, then that don't just have vocabulary, that is your signal to use GraphRAG. So that was the video, guys. If you liked it, please like, share and subscribe, and I'll see you in the next one.